Hello, welcome to this part of a tutorial. Today we're going to look at an entirely different package, although still a product of the Petroleum Expert Group. Today we want to look at PVTP package, PVTP for pressure, volume, temperature, and then the other P for package. So this package it is specifically for looking for doing compositional analysis. You want to look at the composition of your fluid and its behavior, study it, and then conduct some analysis on it. Then this is the best package for you. For those of you who have been asking for tutorials on compositional analysis for EOS model for Prosper, to do that, I bet you'll need to do this first. So that's why I've decided to do this first before I provide that tutorial. So this is actually in preparation for the requested tutorial, which will come in no distant time. So let's look at the environment. So this is the environment. I've not created a new file yet, but if you look at it, you'll see some buttons that have been disabled and some that are actually there. Like look at the menu, you'll see file where you can open new and all that view. So I'll just go ahead and open a new file. And then see we have more options in the file menu. So we'll look at file and then we see the usual options. New, open, import, and all that, save, export. And then we have the options. Like every other Petroleum Expert software, this is where you start from. The options, where you define your model, the type of fluid, the maybe correlations we'll be using, the completion data, and all that. And then we have the data where you enter the components which you want to use, the components of your fluid, like C1, C2, like that, blah blah blah. Then this is where you do some calculations, phase envelope, and all that. Critical point saturation. You can look at the drop down, the main options. Then here you do your basic calculations for wax and hydrate formation, so you can determine the pressure and temperature at which these will occur, and then you can also calculate the minimum concentration required to inhibit hydrate formation. Then you can add streams, edit streams from the same component, and then just when you're doing your study, you'll need some of these. So this is where you generate your reports, and this utility is actually very important, especially as the EOS model, equation of state, EOS model, which we want to look at. That is what the compositional analysis is all about, equation of state. It does not actually account for mass, so you'll find this very handy when you're doing these type of study. So the mass balance calculator is very, very important, very good. It helps to at least so that you know if your whatever you're doing actually respects the mass balance stuff, mass balance equation. Mass in should be equal to mass out and all that. So, and then database, the components which you're going to use in this software is actually stored in a database. So there's a default database that comes with the software. If you're not comfortable with that, or the number of components you have there is small, and maybe you want to extend the component and add more data points, more data points, then you can also create your own database, and then you can set the directory to it and all that. This is where you do those things, and the normal window and the alt. What you have here in the toolbar menu, it's basically the same thing here, but here it is represented with icons and buttons and all that, while here you have more of write-ups, so it's the same thing you have here. So having said that, that's just for the environment. Let's go back to let's look at the data we're going to use for these simulations today. Now I have data here from well XYZ, and let's look at the data together. The report was generated in 2021, and we're told that the reservoir pressure is at 4,894 psi. The temperature of the reservoir is at 267 degrees Fahrenheit, and the reservoir is about 9,500 feet deep. So we have components here with their mole ratios. So we have two impurities, nitrogen and carbon dioxide, And then we have few components: C1, C2, C3, C4, up to C6, and then we have lumped components. The other AVNs joined together. That's what we mean by lumping. So just instead of representing them individually, just join them together and represent them as just a single component. So that's where this C7 plus comes in. C7 plus means from 7 downwards. Okay. So we have we're also given the molecular weight for the AVNs, the lumped component, and then its gravity. So we have the CCE, that's constant composition expansion data at the reservoir temperature. Okay, so we have that, and from this data we're told that our reservoir pressure is this, that we know already. Then we're told this is a saturation pressure. Okay, wonderful. So we also have data for saturation pressure here. Okay, so we have density, viscosity, all formation volume factor, and then we have separator train. From what you're seeing here, we have 3 stages, meaning the fluid was actually flashed through 3 separator stages. The first one at a pressure of 290 psia and temperature of 149. The second one at 22 psia and temperature of 153 degrees Fahrenheit. And the last one at ambient condition, at surface conditions, 14.7 psia and 60 degrees Fahrenheit. Okay, so that's actually very wonderful. I think that's all we have. So we've seen the data we have for this model. So let's just go straight to work and model our equation. Okay, so let's go. So the first thing, like every other petroleum expert software, is the options. So you go to options, click on options, and you have this screen. Alternatively, you can click on this where you have the PVT. It also brings up the options. So we're doing equation of state, so we'll leave this at equation of state, not black oil. And then we let our equation of state model be the Peng Robinson. We have another one there, the Save Redlich Kwong model, but we're going to use the Peng Robinson. So the other thing I want to change is the volume shift. So I'll set this to yes. Okay, the volume shift is just to help adjust the densities. Yeah, just some parameters to adjust the values of the calculations we're gonna do, the iterations and all that, the matching, just basically the densities in order to get a better match and all that. So I'll click on OK. The other information here, you can fill them, but they are not important for my simulation for this tutorial. If you're doing this for a company, you might want to supply the user information, the company, the field, the location, the platform, and then the name of the analyst, which is of course yourself. Then some comment and maybe a date stamp and all that. Like I said, it's not important for my tutorial, so I'll leave them blank. Now the next thing which you'll want to do is maybe to adjust the unit. From my data which I have here, I have discovered the pressures actually supplied in PSIA. I think the default in Petroleum Expert should be PSIG. So instead of doing the conversion manually and entering it, I might want to just set the unit for pressure to PSIA so that I won't have to be converting and all that. So if you go to options and unit, it brings you to this. Alternatively, you can click on where you have these units: kg, pound, kilogram, pound, feet, and mass meter. So if you click on that, it brings you to the same. You have the same screen. So you go down, you'll see pressure, and like expected, it's unit, it's PSIG. So I'll change that to PSIA and click on OK. So I'm done with that. The next thing which you have to do is to define your component. So let's go straight to that. So the components will be defined in data. I'm going to use select component from list. So the list is actually from the database which I'm using. I'm using the default database that comes with the software. So I've not added any data point and all that. So I'll just click on select components from list. And then I have my components here. These are the hydrocarbons, the pure component. Then we have the non-hydrocarbons, the impurities, of course. And then we have no pseudos yet. You'll define the pseudos later on. But if you've added data points to your database, you'll have them here, the user created. So you see mine is blank. I've not added anything. Okay, so from the data we have here, we know we have two non-carbon components. That's nitrogen and carbon dioxide. So just click. All you have to do is just click on them. You don't need to hold down the shift key or anything. Just click on the component. Okay, if you want to deselect any of these, click on the component again and it will be deselected. So click to select and click again to deselect. As simple as that. So we have C1 as one of the components, C2, C3. I have the two variants of the C4. There's the ISO and the normal butane, and also the C5, the same ISO and normal. And then I have C6. For the C7, I'll omit that since it's lumped together. So I'll define this as a pseudo component. So I'll come to number of pseudo components and then I'll just enter 1. Okay. Now, having done this, the next thing which I'll have to do is to enter my composition. The composition is actually supplying either the mole ratio or the molecular weight for this component so that the software can use that for its calculation. So I'll click on enter composition and then I have the screen. Now you'll discover we have molecular weight already supplied. Yeah, we have that. That's from the database. If what you have here you're not comfortable with it and then you have your own molecular weight, you can come to these composition input options here and then change it from molar, which is what the software is asking you to supply, the molar percent, the molar either as percent or fraction, any of those, it's the same thing. Okay, so you can decide you can change it from that to molecular weight and then the software will expect you to enter the molecular weight and I think it will do the calculation for the molar percent itself. Okay, so but I'm going to use molecular percent. I'll supply that and use this ones. I think they're pretty standard. These molecular weights are pretty standard, the same across. It doesn't change except for the pseudo components, which you'll have to do that the calculation yourself and all that. Maybe if you supply the information to the software, it will do the calculation. Okay, so let's just go straight to entering the compositions. Instead of just sitting down to type like 0.38 and all that, I could just go to my data which I have here and just copy and paste. I think they follow the same trend. So I copy Control C. Since I have nitrogen, CO2, C1 and all that, just come here. I can delete this or so click on these and then Control V. That's all. I don't have to sit down and type. It saves me a lot of typing. Okay, the next thing is I'll love to enter the molecular weight of my pseudo component that I have as 228. The next thing which I'll have to do is to supply the reference data. I'm going to use the reservoir parameters as my reference. So the reservoir depth, the reservoir pressure, and the reservoir temperature. So the temperature is at 267. The depth is at 9,500. And the pressure is 4894. 4894. Okay, 4894 psi. So I'm done with that. Now there's something you'll have to notice. After you've supplied the molecular percent, if you look at this, you'll have total molar 100%, remain at 0, meaning what we've supplied is actually okay. Sometimes you supply this and you discover there are some remainders, maybe a positive remainder or a negative remainder. That means you should actually look at your molecular percent and maybe consult your lab engineer, your lab technician or lab scientist or whatever, and ask why we have that discrepancy. And you can actually, ask why you have that discrepancy. You can do some adjustment and all that. Okay, so we're done with that. The next thing which we'll have to do is to supply our pseudo components. Unfortunately, our data did not come with those pseudo components, but I guess the person that supplied this omitted that because actually it should come full composition instead of this lumped component. But we can proceed and see what we have. So I'm going to go to pseudo properties, and here we're going to do some calculation. So we can calculate the critical temperature, critical pressure, centric factor, and all that. But first, we need, out of these four spaces, we have four areas where you can supply data, but you need at least three of them to proceed. So I have my composition already, I have molecular weight. The next thing which I need is either the specific gravity or the boiling temperature. Fortunately, I have gravity here, so I'm just going to use specific gravity 0.858. Okay, once you're done with that, you can use correlations to calculate the other values. So I'm going to use the Petroleum Expert to calculate the boiling point, boiling temperature, and then use the TWU, and Edmistar correlation to calculate the others. So this is what I'm going to do. I click on calculate values and it populates the screen. That's actually very wonderful. But there's something. The equation of state model will not on its own predict the right densities for the pseudo component. So it needs the help of a standard correlation, which is based on the conservation of mass. And those correlations, we have about two of them. We have the standing cuts and the clustered. So if you look at the screen, we have density method, standing cut, and clustered method. So in order for you to have a good match, it's good that you match these densities. So I'm going to use this auto match button to match density so as to get something to get a better value. So what the auto match does is it iterates on the densities of the AV components. Fortunately for us, we have just one of those. So it will iterate on these densities until it matches either equal to, or the error, the difference is very small, until it matches what is calculated using any of these correlations. So it's actually very important to do that. So I'm going to click on auto match and then look at the percentage difference. Just keep your eye here to see what you have at the end. So click on auto match and allow it to calculate. So after 3 iterations, we have difference of minus 0.0, 0.0 is 0.0, whether positive or negative. Okay, so we have that, and meaning we have a perfect match. If you were observant, you discover that some of these values are changed during the iteration. Okay, so since we have these, the next thing which you'll have to do is to check if actually what we're doing is anywhere close to what we're expecting. Now we have some data supplied to us. Um, we know our saturation pressure, we know separator train data with GORs and all that. So let's see if these models so far can give us anything close to these values. So that's where the quick calculation comes in. So I'm going to go to quick calculation and then check some of these. So first, let me check my saturation pressure, if what I have can predict it. So I click on calculate and I have 2975. That's close, but not very close. We're expecting 3540 and I have 2975. Or at least it's close. So let's look at other this thing. So let's look at the phase envelope, calculate this. We have this, but how do we check if this is correct? So let's just supply test point, and our test point will be none other than our saturation point, saturation pressure and temperature. The temperature is at 267 and the pressure is at 3540. Am I correct? 3540, yes. So I'll click on OK, and wow, the point is above, so meaning it's not accurate, but at least it's somewhere close to above our recondent bar. Okay, so but from everything we're seeing, we see it shows that we are actually on the line. We are not very far away from the actual. Now the essence of these initial iterations or initial matching is the actual matching is actually coming where we'll use the supplied lab data to match, but the sense of doing this is so as to get as close as possible to the actual stuff, so that when we're doing the actual matching, it will take it will be more accurate and consume less time. So that's the essence of all this. So I'll go exit, and then let's look at the separator stages. So the data I have is flashed through stages, not directly to standard conditions. So that's why I'm going to use this. So I'll click on calculate, and then I'll supply these data there, pressure and temperature, just this once. So for the first stage, I have temperature at 149. Can I adjust this? Let me adjust this a bit so that I'll have more space. Okay. Okay. So I have 149. And next stage is at 153. Next one is at 60. Now for the pressures, I have at 14.7 for the last stage, 22 for the second stage, and the first stage is at 290. Okay, so the next thing which I'll have to do is just to calculate. Now the density method is standing and cut, of course, what I used before. So I'll click on calculate, and I have this. Now let's compare that to the data I was given to us. From the data we're given, expecting GOR for this first stage to be at 788, but we're having at 764. That's not too bad. For the second stage, we're expecting 128, we have 127. Of course, we're actually very close to, very close. And then the other one, we are expecting oil density for the last stage to be at 844.9, but we have 843.3. That's pretty close. So note we're using these ones, not the total GOR. Okay. So I'm also using this, not the one calculated. Because standing and cut says it should be at 842, but we have 843. So, and then you can also look at your gas gravity too. Where is the gas gravity? Okay, gas gravity. So first stage 0.76, we have 0.75. Second stage 1.474, we have 1.311. So what we have there is actually correct, at least. So you're done with that. Since what we have is pretty much, it's very close, we can actually store this now. So what I'm going to do is store these values as it is and use that as reference. Now the implication is this: if we match in the future, if we proceed with the matching and we have worse values, you can revert to this initial one that was close, and then you can revert to it, and then maybe use a different method to match and to see if you can improve upon it. So instead of you add something good and then as you progress you add something bad and there's no way of going back. So instead of meeting a dead end, you can actually go back to something that which was preferably good, or yeah, at least good, manageable. And then from there proceed again, check different parts, different methods, and to see how to improve upon it. So I'll store these values, then I'll ask my simulator to use these values for whatever calculation it wants to do proceeding. So I'm done with that. Now the other thing which I'd like to do is to split this component, although I do not have the actual data to know how this thing looks like, but it's good practice. You can split or you can leave it. Yeah, it's okay, you can leave it. If you want to leave it, no problem, but let's see how to split. So in case you have the full composition and then you'll want to split to see if it follows. So the way to do that is I'm going to use my split slash profile section. So instead of splitting in two, I'll use the advanced split. Then the method is the Wheatstone method. We have others, Petroleum Expert 1 and 2, and so I'll go click on advanced, and then I have this. Sorry, my screen is not long enough. There are some. Method is Wheatstone, would calculate to end, and then extended properties, molecular weight. We're having Petroleum Expert. Let's change this to Wheatstone, and also the specific gravity. We'll change that to Wheatstone. So to use a consistent correlation. And then we have our components here with their molecular weight, specific gravity, and mole percent. But then let's observe something. If you look at the composition here, discover the mole percent is actually reducing from C1 down, from 43 to 7 to 5 to 2.9 using the normal variant. Then we have 1.6, 2.23, but for our C7 suggested here, we're having 3.1. That's large. So we have to tune this to follow the trend. So it should be something less than 2.23. That's the value we have for your C6. So the way to do that is to adjust the alpha factor. So I'm going to change it from 1 to 1.1, and then I'll recalculate the splits. I'm still having 2.65, which is greater than what I'm expecting. So I'll change that to 1.2 and recalculate again. Now I have 2.20, which is at least lower than um, the C6. So I can proceed with this. Now I'll have to copy some of these components to my pseudo components here. And what I'm going to do is I'll need about 10 of these, and I have more than that, but I can determine the actual number I have because of my screen. But I can take 10, 10 should be okay. And then I do even splits. So if I click on even split, I have copied the component. So these are now my pseudo components. Very interesting, right? Now we can proceed with this. I can exit and save, and then maybe perform the quick calculation again to see if we have something better. So start with saturation, calculate. Now I have something better. Now 3.1 as opposed to 2.9. Yeah. So 3.1, I'm still expecting 3.5. Well, yeah, but there's an improvement. So I can look at my phase envelope and calculate this again. Now it's actually here on the recondent bar. Yeah, that's wonderful. That's an improvement. Okay, and then if I look at my flash through separator stages and calculate again, I have 879. Let's scroll to that. As opposed to 788. Now I think it's overestimating now, but that's not a problem. Okay, so at least we've seen that. Now since we've still not gotten a perfect match, you can go to the next thing which we can adjust is our BI coefficient, binary index coefficient. So we can adjust this ones to see if we can get something better. So I'll click on this and then use the chevron method to calculate new values. And then I can quick check again. Let's see if we get something better. Now we have 3.6. Wow. I think we are actually improving. That's good. Okay, so that's not all for a quick check. Let's check our phase envelope again. Calculate. Now we have a match. Wow. That's still not perfect. It's a little below. A little below. Okay. That's not bad. Little below meaning uh, the maximum values are too high. Okay. Let's look at flash through stages and see what we have there. Calculate. Having pretty much the same value we had for the last one, but that's not bad. Now the way to adjust this is since our point is now below our first envelope, we can adjust the maximum points, the maximum values for this. I think the maximum value is about 0.13, 0.13. So I'm going to change that to what? We're going to 0.01. Let's check 0.01. Let's calculate this again. Face envelope, that's what I'm interested in. Calculate. That's bad. 0.01 is not good. So I'm gonna calculate again and maybe set it to 0.1. Oh, did I set the values? Okay, I did. So I'll set it again. Calculate. Face envelope, calculate. Still not perfect. I think it's pretty much what I had before. Uh, I could leave it at that, but let's see if we can. Let's see 0.05. Set the values. Quick check. Quick check. I think we have it now. Ooh. That is. Yeah, I think it's closer. Closer. 0.05. 0.05. Okay. So, but you can still adjust it if you like. Maybe to let's see 0.0. Let's see what happens to 0.04. Yeah, 0.04. We'll have something better. I think that's yeah, I think this is better. 0.04 is better. The 0.045 I think should be the best. Okay, 0.04 is good. That's a match. That's a match. So we can proceed with that. We can also check for the other ones. The saturation pressure again. We have 3.5. I think we had 3.6 before, so this is 3.5. So we have a better match. We can also check for the stages. Let this. We have 884. I don't know if there's a reduction there. I didn't really study these values. Okay, so but at least we've seen how this goes. So from this, I think we can stop here. So I'll exit and save. So that is where we are at the moment. The next thing which you'll want to do is to supply your lab data. So where you do that is your data. You go to enter lab data. So just supply the data and proceed. I think we're running out of time. So I'll start with the saturation pressure, the saturation values. So these are the values. You have the temperature was at 267. The saturation pressure is at 3540. Yeah, correct. And then density at saturation is 634. That's okay. The next one is the constant composition expansion values. So that's basically all of these. I don't have time to type, so just copy and paste. Copy, Control C, Control V. Then I can remove these write-ups. Excuse, please. Okay. Okay. So the temperature is constant at 267. Now liquid dropout. This is actually saturation. This is a bubble point liquid. It's actually liquid oil. So the liquid dropout is actually suited for retrograde gas condensate scenarios where you have dew points and then liquid dropping out from the gas. So we don't have this data, of course. From this, we don't have the data we have is we have oil viscosity. Okay, we have oil density. Do we have somewhere for that? No, we have oil viscosity. So I'm gonna copy the oil viscosity values. Or copy oil viscosity. Center points, supply that. I have value for oil formation volume factor. So copy that and supply. And then I also have values for what again? I think that's all. I mean density. So yeah, there's density. So I'll supply my density values. Okay. So copy this and supply here. Okay. Now that's for that. I don't have these. This is also suited for retrograde. So I have separator condition. So just go to my separator and supply those values. So I have temperature at 149, at 153, and at 60. Pressure at 14.7, at 22 and 290. Okay. Gas oil ratio. Can I copy this? Yeah, I can just copy and paste. So copy. Okay, oil density. I have oil density 844. Okay, I think that's all. These are the ones that are values. Okay, now the next thing is to do your matching. So to match, we don't need all this data to match initially. It's good practice to start your matching with the minimum data, and according to the Petroleum Expert and literature, the minimum data for matching should be your saturation points. This ones, okay. We need for the CCE, we will not need oil density, so we can exclude this from the data we're going to use for the initial matching. The oil formation volume factor is very prone to error. Any small error here will affect our matching very much, so I'm going to exclude this for now. Okay, then what again? Let's look. Okay, that's for CCE. Let's look at our separator. Let's exclude the last two data for the gas oil ratio for the same reason. and set the first one to a smaller weighting for the same reason of error and all that. So I'll set that, and I think that's all. I can make do with this ones. So let's go straight to the matching. So I do okay, and then the matching proper. So you go to data and regress. So we have these. I'm going to select all these ones. Okay, and then I'll just want to match the TCs, critical temperature, pressures, and all those ones. And then that's all. So I go to regress, and I'll select. Now for the the critical points, I'll select all, but then I only want match for the pseudo components. I want preserve for the pure components. So I'll clear the pure and then allow just pseudos. So if you go down, you discover you only have the pseudos selected. Okay. Okay, I'll not need any of these. Then for the volume shift, I'll select all except for the non-hydrocarbon components. And then for the binary interaction coefficients, I'll set all pseudos with same multiplier. And now I can regress. So let's regress. So if you notice, you discover the value, it's actually reducing. So we set it at 200 iterations. We can allow that to complete, or you manually stop it yourself. So I'll just allow this to complete, and we'll get back after that. And our calculation is complete. So once the calculation is complete, the next thing you'll have is this screen here. So I'll just look at maybe the boiling properties. I'm not going to calculate using this. Now, notice calculation method is flash straight to stock time. What this means is there are no separator stages, so you're just flashing directly. If you use this, it will affect your readings, your calculations for GOR, oil formation, bone factors, and others. Since we actually flashed through separator stages, what I'm going to do is I'm going to change this to use separator train. Now, you discover what you have here. You're having just the value for the last stage, last stock time condition. So I'm going to supply what we actually have, what we're expecting, so that we get more accurate values. 22 and then 14.7. Then I have 60, 149, and 153. Now I can calculate. Okay, so that's what we have, and you can click more to check. Okay, that's all for now. Now the next thing which we have to do, which is actually very important, is sorry. That's not all. That's not all. I'm sorry. We actually matched this, but we didn't match our viscosity data. So please let's proceed with that. So I'm going to calculate viscosity, the same, regress, and then select all of this. So we're using correlation. So 200 iterations should be too much. I don't know, but let's just proceed with 200. So I'll go regress. So the same thing. I think you're good to go. Okay, exit and save. Okay. Now let's do the calculation to check if what we have actually done is accurate. So first I'm going to do for face envelope. You look at this, it's actually correct, very but then that's not all. Let me do this. I'm going to change this from manual entry to auto and then calculate again. Okay, so if you look at this again, see it looks pretty clean and very interesting, pretty clean. Okay, so that's that for that one. Sorry, I don't want to do this. Let's look at calculate saturation pressure. So I'm going to use user selected. I just need saturation pressure at 267 degrees Fahrenheit. Go calculate and calculate, and hopefully you should get the correct one. I think we did 3540.0 0 to, that's correct, man, and our density is also correct, 634, 634. So meaning we have a very wonderful match. Wow. Okay, so let's look at the other one again. We can also do this constant composition. So let's check that. Constant composition from, I think the temperature was pretty much constant. Temperature was constant, yeah. So I'm gonna use one value for that, and then the pressure, I think we are from about 1,000 to 6,000, but I can maybe calculate from 500 to maybe 7,000 at any value, but it should cover the entire range of what you are actually doing. So that's the idea. So I can use whatever values, maybe 100, 200, 50, 20, 30, whatever. It's left to you. So I'm still using my separator train. So I'll go calculate and then calculate. Ooh, wow, that's wonderful. So you can plot this. Wow, look at this. We have perfect match for oil formation value factor. You can see, if you look closely, you see green points here. I think that's the only green point we have. So we have a perfect match for that. You can select variables. Let's look at oil density. Okay. We also have a perfect match for that. And not so perfect, but at least it's wonderful. You see the green points, and our data point is passing through the green points. So we can look at, you can select whatever variables you want, and you check. Just select. Then we have, I think I've checked for oil from, not just that. Anyway, you can check for other values yourself. So that's for our calculation. What else do you want to check? I think you're done. Okay, let's look at separator. Let's look at our separator. So if you calculate this, let's see. Yeah, calculate this. We have 846 for, as against 844. We have 846. Not too bad. And then our density, we have 791 supposed to 788. Not bad. At least we've seen the other ones are actually very good. So 791, 844. That's all. That's all we have. Okay, we can also look at what again? Is there anything to look at? I think we're good to go. We are good to go. So that's how to do that. So that's where I'll stop for now. There are other things. Okay, let me just do it at once, and then maybe I'll split them into different tutorials later on. Browser is coming up. Okay, you can split them into different tutorials later on. So you can also export this data. Now, let's say you want to use export the black oil table and maybe use it with other softwares, or use it with Petroleum Expert Prosper. How do you do that? First, I'd shown you something. I had shown you our where is that view properties. If you go to data, view properties, and you look at this, these are your black oil properties. Yeah, black oil properties. And then if you're looking for impurities, the accumulated vapor, is it accumulated vapor? These are your impurities which will enter into your Prosper software. So you use this, you have formation GOR, CGR, density, gravity, all that. So volume of oil, volume of gas, mole ratios, and all that. So to apply this and this, but you can also export this. So how do you export? You go to exit and save. Go to file, and we have exports. So click on export, then you can click on black oil table. Click OK, and then you can calculate. Just enter a range of pressures for which you want to export. So pressures like, let's say, start at 7,000, 6,000, 5,000, 4,000, 1,000, 4, 3, 2, 1,000. Oh, sorry, had to be 1,000. And then 500, maybe 250, I don't know, but whatever. So once you've entered that, the next thing is just to click on calculate. Oh, sorry, I didn't supply the temperature. Table temperature is at 267. Okay, 267. Okay, so that's what you have. 267. You can click on this, calculate all, or you click on calculate table. Now it's possible to enter to have more than one table. So this is just, we're just using one table here, and then all you have to do is click on, I'll use calculate table, and it's done calculating. So we have all our values here. Okay, now once you're done with this, notice I was using separator train. Since you're using separator train, let's stick to that. So once you're done with this, you select the software you want to export for. We have Embal here, Prosper. Embal and Gab uses the same. So if you look at this, you have oil, gas, and condensate. We're not doing condensate, doing oil. So, and you can export for Prosper. Choose Prosper, then choose the variables you want to export. Maybe pressure, oil formation, GOR, density, whatever. Just choose them, and then click on export. So you can export current table, all tables, but I'm using just one table. So export current table, export, and the next thing is it brings up this file dialog, save as file dialog. So you choose your location where you want to export to, and let's say I want to export to desktop, and then just choose a file name. I'll call it oil, and then save. Okay, that's all. So you can do that. You can do that for other softwares. So you see Eclipse black oil format, Eclipse compositional format, and all that, CMG and all that. So that's all for this tutorial. Tell me what you feel. Are there questions which you have? If there are, please do all to ask. Use the comment section. If you appreciate our tutorial, please tell us so that we know that it's been of help to you, maybe in your career and your work and your studies and all that. So thank you very much for watching. Do also subscribe. More and better ones are coming. Goodbye for now. Bye.